damage, but they had trouble with electricity, so they would only call for very short visits. I guess.
I'm still trying to get a feel for how strong the current hurricane. I mean, it looked like a beast coming in, though. I don't know if it. I saw what it did to the baseball stadium down there, which is amazing to look at. Though I don't know how bad the impact is in general.
I think that was planned.
Planned.
Yeah, the Rays have been looking for a new stadium for like 15 years. So, you know, this is the perfect opportunity.
Dan, has anybody reported Skynet being awful slow for a couple days?
Me always. I don't know. Let me pop in here to Skynet. Now, some pages in the here, let me share my screen. Oh, I am sharing. Okay. Some pages can be slow to load. So this is part of the Skynet 1 infrastructure, which we're working frantically to replace as we build the Skynet 2 system. Like one feature is the page freezes until the sample images here load, which is, if they're just 1K by 1K, it's not a problem. But with some of the bigger chips, that can really slow down and you get stuck on a page and you don't know why. It's because it's loading images down below. That won't be in the Skynet 2 system. But
yeah, the last couple of days when I go to to get into that page, sometimes I've waited about 5 or 6 minutes.
Ooh.
And then all of a sudden it's like it's there, but it's just taken an awful long time.
I wonder if your sample images are like, I think Hampton-Sydney College has a really large format camera. And you got to remember, this page was designed 10 years ago when we're just using 1K by 1K chips everywhere. But now that we have like 4K by 4Ks at various locations, if you have like 6 of them here or however many, that can slow the loading of this page.
Okay.
Sometimes it won't even bring up the page if those are your most recent samples. I'm not saying that's the problem. There are other reasons why we can have slowdowns, but it's that's one of, if that's the reason, there's not much I can do. But I am, you know, be aware that we're busy building Skynet 2.
Yeah.
And so I just gave a presentation to the DoD. I was going to show you some of this stuff at the end if there's time. Here's just a little, maybe I can make this big. I'm not prepared to show the Skynet 2 system, but I included one slide here. And so the Skynet 2 interface, there's a lot to it. This is just, you know, one small piece. But this is, if you want to make an observation, like a mosaic, for example, all you have to do once you've picked your target, and I'm actually not super familiar with how to move through the new interface yet, but you just basically draw a box and it designs the mosaic for you. You can pick the angle and the number of tiles that you're willing to have, and it sets the overlap. And it's really, it's just one of many sweet features on the new interface. Yeah, you say, I want to image this area this big. Oh, my camera doesn't cover that. It will automatically build the mosaic for you. It's cool. And in the 2.0 page, it'll automatically put it together for you too. Anyway. Other things. Does anyone have other gripes and complaints? Get them out of the way.
Yeah, actually, no. Oh, you mean related to Skynet? No.
Not in general.
I got a lot of problems with you people, and now you're going to hear about them.
Yeah, it's we all have gripes and complaints about various things, politics in particular, I'm sure.
My friend Costanza. Whoa.
All right, so let's see. Well, last time was our Kate Meredith joined us. We always give her half of one of these to talk about accessibility issues, which you know, we take seriously for both selfish and selfless reasons. Selfish reasons that having this stuff built into our grants helps win the grants, and selfless because it's the right thing to do. But as we talked about last time, most of the interfaces and tools that we've built have put some thought into accessibility. They're compatible with screen readers, they're large text and high contrast options, and we're moving to graphing tools that don't yet talk, but can, they have that capability. Anyway, so you heard from her, and if you have any students with accessibility needs, or actually the takeaway was to look for these students, like on day one, spend a couple minutes, and if you can find these students, we're desperate to work with them. And then during the bit that remained, we started Lab 3. We did the end of Lab 3. So Lab 3 really has two components. It's called the Galilean Revolution, and kind of the Galilean Revolution part of it is whether we live in a geocentric or heliocentric universe. And that part's the kind of quick and easy part using phases of Venus. It's currently at the end of the lab. This lab 3 is the next one on the schedule for revision, and we'll probably move that up to the top of the lab. I'm also working on plans to make the labs more modular. I'm actually starting to plan for the post-WebAssign era. I know a lot of people aren't happy with the WebAssign tool when there are things like, capabilities of things like Canvas, Moodle, et cetera, have improved. So we're beginning to make plans in that area. Anyway, one of the things is we're going to try to increase the modularity. We're going to try to make these things edible to instructors, but I'm off target. Let's bring up Lab 3. I think I have it here. Okay. So yeah, we did this bit here. We did the first background section and this very last bit here. Goals. Let's go back to the goals of this lab. So the last two there measure the phase and angular diameter of Venus and use this information to distinguish between geocentric and heliocentric models of the universe, solar system. We did that last time. So the other larger part of this lab is the Kepler third piece. And although Kepler third isn't really germane to the main line that goes through all these labs, our place in space, our place in the universe, understanding our place in the universe. It's such a key, critical topic in introductory astronomy courses. We had to fit it in somewhere, and it made sense to fit it in here because they can collect the data on moons going around gas giants very easily. And so we built it in here. So goals 1 and 2, measure a moon's orbit around a planet and use this information to measure the mass of the planet. Okay, we're going to do that next. So let's hop to background B. This is where we set this up. You know this stuff, but I'll just explain through it anyway, perhaps as you might to your students, though I'll do this faster. It's all in the videos, of course, in greater detail for them to use as well. But introduce them to an ellipse and some terminology. We have a major axis, we have a minor axis. Show them how they can make their very own ellipse at home. It's very simple, 2 tacks and a string with a little bit of looseness. You can draw an ellipse. Anyway, half the major axis is, you can think of it as the long radius of this squished circle, this ellipse. And Kepler's third law is parameterized in terms of that, denoted A, I guess, for axis. And now Kepler's third, and many things in introductory astronomy, the Kepler's third is really a great example to teach your students ratio calculations. When I teach introductory astronomy, I try to set everything up as a ratio. And maybe once or twice they have to plug in a constant like the speed of light, but I try to avoid those plug and chug problems and set everything up as ratios. And it takes them a little bit to wrap their mind around the concept. But if you really commit to this philosophy, they get used to it, and then it's super easy. It makes calculations super easy. You'll see that here, and perhaps I'll give you some other examples as well. Anyway, Kepler, here's Kepler's third law. P squared is proportional to A cubed. He checked this out for different objects going around different objects. The moons of Jupiter going around Jupiter, the planets going around the sun, and the moon going around the Earth. And this always holds, except with different constants. And he didn't know why you had different constants. That wasn't resolved till Newton came along and invented physics, and you can actually derive what that constant is, and you can see that here. This is actually a simplified version of it. It's actually capital M is the mass of the central body. It's actually the sum of the mass of the central body and the orbiting body. But in all the cases that the students would be dealing with, planets going around the sun or moons going around planets, the central body dominates the mass. So we just simplify it here. So that's the constant proportionality. What that means is if you measure the period of say a moon going around a planet and you measure its semi-major axis, you can calculate the mass of the central body. You can weigh a planet. Now, if you're doing the traditional plug and chug approach, suppose they have the semi-major axis, let's say it's in AU. They have to convert that to meters because G is in the MKS system. So, you have to convert your semi-major axis to meters, and you plug through all that, and period will come out in seconds, which you have to convert to a more, your period will be probably measured in days, but you have to convert that to seconds. You plug that in, and then you can solve for G in kilograms, which you then have to convert into a useful unit like Earth units. I didn't say that very cleanly, but you get the point. Everything that you're putting in would have a unit conversion. What's coming out has a unit conversion, and you're having to plug in these constants. There's lots of opportunity for student error. So the ratio approach is you have a comparison object. So it could be anything orbiting anything. So let's take the Earth orbiting the sun. Even though this lab is focused on moons going around planets, let's take the Earth going around the sun. And you can see that right here. In the case of the Earth, the period is 1 year. The semi-major axis is 1 AU, and the central body has 1 solar mass. And so we have two equations, the generic and for the comparison object, and you take the ratio. And the G's cancel. And again, I apologize. Most of you know all this, but anyway, the 4 pi squareds cancel, and it simplifies to this. So in other words, if you measure the period in years, even if it's a moon going around a planet, it'd be a small fraction of a year, but you measure it in years. You measure the semi-major axis in AU. Also, it'll be a small number because we're talking about a moon going around a planet. But solving for M here, just A cubed over P squared. If you measure it in the appropriate units, the units of your comparison object, it's just one number cubed over another number squared, and you have the mass. Super easy to calculate. Let me give you another example, because you can do this over, and again, you probably do this already in your classes. But if not, I encourage you to really lean into this. Another great example, Stephan's law. The energy coming off an object, proportional, the energy flux, proportional temperature to the fourth, the Stefan-Boltzmann constant sigma times T to the fourth. But if you take the ratio approach, you can say, okay, you got two objects. One is twice as hot as the other. Its energy flux is how many times greater? Well, just 2 to the 4. And so easy. You could do it right in your head, 16. And you didn't have to stick in Stefan-Boltzmann constant or anything like that. And there are many, many examples. Okay, enough of that. I'm probably preaching the choir here on that one. Okay, so that's the prep. So let's go down into the procedure. So here's where we start here, procedure A. This is where we monitor. So this is where we put the observations in a couple weeks ago. Let me check Skynet. I did one on Saturn, one on Jupiter, and I put these in, I don't know when I put them in a few weeks ago, and all my data has come back. And my TAs are telling me that the data is coming back. Sometimes if we have a long run of down telescopes, which we have at the moment, and cloudy weather, it may be a little hard. Or if you're doing this over the summer, which is bad observing in the north and bad observing in our sites in the south, it can be hard to build this up. But most of the time, you put it in 2 weeks ahead and you'll have a full set of data. You really only need 5 or 6 to come back, but the more that comes back, the easier it is for them to see the patterns. Anyway, so they put the observation in. It's one of these things repeats once a day. And here, depending on what planet they picked, and we already talked about Some have certain pluses, some have certain minuses. Uranus is the hardest because the moons are often lost in the glow. Anyway, and you set up to repeat. Okay, so suppose the data's back. What we're going to do, a key thing here actually is, where is it? Oh, it's down here. Once the data's back, they have to check this box. It's only worth 1 point. But if we're doing Jupiter, we're going to track Ganymede. If we're doing Saturn, Titan, Uranus, Oberon, Neptune, Triton. These all have periods of about 1 to 2 weeks, so they're kind of ideal for this activity. And they select which moon that they're going to measure. And although it's only worth 1 point, this sets the auto grading for the rest of the lab. So it's actually worth a lot of points. If they pick the wrong moon, if they're doing Ganymede going around Jupiter, but they collect Titan, they're going to lose a lot of points later down. Just something to be aware of. Then they have a table here where they're going to put in the date, the Julian date of their observation. We're going to plot this on a graph. So we don't want year, month, day, hour, minute, second. We want it in some kind of straight up number decimal form. So we're going to go with Julian date and the angular separation of the moon from the planet. And from that, we'll determine the orbit. Okay, so let's go to Afterglow and start to play with this here. Oh, start with Saturn here. So here's a sequence of Saturn observations. Guess I should have preloaded them. There we go. And Saturn's in there. As I said before, we can adjust the brightness and contrast. That's too much. I lost all the moons. So I'll back down the saturation level. Maybe I'll just adjust it using the wheel until I'm happy. Yeah, tamp down the planet a little bit so I can see the moons. This one right here is Triton, but the only way you know that is by going to Stellarium. So and they learned how to do this in Lab 1. A lot of the things that they did in Lab 1, you may be wondering, why were they doing this? Why were they doing that? Other than it's something they could do. They're building up a toolkit that they use. So I don't have it open right now. Let me open up Stellarium. By now, they should be pros at this. Okay. Remember, for this activity, we want to set it to UTC as our time zone. Turn off daylight savings time. Okay, so everything's in UTC. It's only in Lab 2 that we use local time because it's kind of a day-night, length of day kind of thing. Location doesn't matter because we're just going to turn off the ground and the sky. Let's head over to Saturn. And if you put in equatorial mode, it's more likely to match your image, or your image could be 180 degrees rotated, because a lot of these are German equatorial mounts. And so on one side of the sky, the image is straight up, but on the other side of the sky, it's upside down. So sometimes you may have a 180 degree rotation. Okay, and then what I normally do is I go through each of my images getting the dates first. Let's go over here. So the second tab down is where you can get the dates. Center Julian date, it's right here. They can copy that out and stick it in the lab for each of their images. And right here, we also have the year, month, day, hour, minute, second. In Stellarium, you can use either. Let's, you could do, here's the year, month, day, and here's the Julian date, the modified Julian date. So if you copy that, I haven't actually tried it with the Julian date. Let's see what happens. Oh, it's moving so quick. Maybe I need to. pause the clock. Let's try that. Did it paste in there? It didn't. Interesting. Copy. Oh, I'd have to type it in, I guess. Well, if I have to do that, I'm going to go over here. Okay. 2019, October 17th is when this image was taken. Around 0:50. Seconds don't really matter. You can even turn the clock back on. And that matches very nicely with our image here. The date, time out of there. Titan, Ria, Titan, Ria, Dione, Tethys. That's about all I have. Anyway, this one we just need Titan. So there's Titan. And after you do it in one, you don't actually have to do it in every single one. Let me go to the next one. It should be nearby, or I may have to do a rotation. Oh, here's a little hint. If I come here, come to the gear, sync display settings, then whatever display setting you fine tune to get the moons here will now be imposed on all the images. So let me go to the next Saturn again. See, it automatically set the display settings. This one tightens down here, so we've had a rotation.
Dan, are you sharing your screen or am I having problems?
Oh, I hope I'm sharing. It says I'm sharing. Am I sharing, everyone?
I see you.
Yeah,
Yep.
at the top, are you clicked on where it says Dan Reichardt's screen or where it says meeting?
Got it. Thank you.
I've done
Good.
that before.
If I'd gone this far without sharing, I would have been very sad. And disappointed in all you for not letting me know for so long. Okay. Here I just rotated that 180 degrees and you can see, that's Titan. It's moved a little bit. Let's try this next one. These are just 1K by 1K, so they should load a little bit faster, but it all depends. I'm at home, so it all depends on my home internet. Oh, come on. This is really kind of sad. There we go. This one has an offset issue. It also looks like need that rotation, but see, it's moved even more from here to there and so forth. So, you could track it going around. You don't have to look it up in Stellarium every single time, though you may have some rotations that you have to take care of. Okay. So that is moon identification in Stellarium. I already showed you where to get the Julian dates that go into the lab. And then it's just about angular separations. And let's do this one here, for example. And then I'll also show you Neptune as another example. So again, it's the same measuring tool. They used it before to measure the sizes of things. Now they're going to use it to measure distances from Titan to Saturn or vice versa. But here we can actually turn on, they can eyeball it, but we could be more precise. There's the centroiding thing. And there's two algorithms, a basic algorithm for point sources and a special algorithm for planets. It starts by default with the planetary one off, so I'll click on the moon first. Just got to get it close and it finds the actual centroid. And then I'll turn on the planetary algorithm and I'll purposefully click off the center and it should, see, it popped in. There's a different algorithm for centroiding extended disks than point sources, but we have that coded in there. In fact, if I adjust the brightness and contrast and come back to here, oh, it didn't actually do a very good job. Sometimes on Saturn, it gets a little bit lost. Curious. Let me put the brightness and contrast back. I'll try it one more time. Of course, it helps the closer you are to the center. Okay. Yeah, if you click off the planet for planetary centroiding, it does hang for a second because the algorithm's a little slow. There, that's probably closer to the center. Oop, that was the point source. Let me try one more time. Planetary centrating is off. So I'm going to click on the point source, turn planetary centrating on, try to get near the center. Yeah, that locked in. Okay. Anyway.
Dan, quick question, why do it that way as opposed to going from the planet to the moon?
Just because, you know, you can do it either way. Just when you first come to this window, the planetary centering is off by default. So I normally start with the moon. But if you have it on, you can start with the planet.
Okay.
And then turn it off and do the moon. I got 68.981 arc seconds, and that goes in the lab in this column. So days and arc seconds. Sign their name. Okay. And oh, let me show you Neptune as well before we move on to orbiting, modeling the orbit. So Neptune is the easiest because there's only one visible moon, so you don't have to use stellarium. But sometimes students get confused as to scale. It will always be right next to the planet. I've never had these, well, not never, but usually. I was just doing stuff in this morning. It was way faster. So maybe it's because I'm on Zoom and all the video. I don't know. I'm at home with weird internet. Jeez, come on. Here we go. So Neptune here, and that's the moon Triton. Students will often say Neptune and then take the brightest star in the image as Triton, but no, always really close. Here they're well separated, but if you image with a low quality telescope at a low quality site, they can be blurred together. And sometimes they can be blurred together too much for the centroiding to actually work, in which case you just have to eyeball it. Now these are separated. And so, you know, I can use the centroiding algorithm. But I can also just turn centroiding off and eyeball it if I have to, if they're blurred too much together. Okay. So then in the lab, once you have this, we're going to go to the Astromancer tool suite. And I think I kind of previewed this a little bit last time. Go to the tool called Moon. Here's a tutorial on how to do it. Just clicking on the website. You can use the old or the new. Here's the new, and it remembers what you did previously. So this is where we left off last time. I have a file and I copied in. Basically, I went through all the Neptune data that was just there in Afterglow and put in the Julian dates and the separations, and you can just copy and paste them in. And let me reset the model here. Okay, actually, let me go to the lab and explain what we're looking at a little bit. So this is from the old tool, but on the x-axis, we have time and Julian date. The y-axis, we have angular separation. So this is an example of a moon that crosses its planet. Here it is far away. It crosses, like the Jovian moons cross the planet, goes all the way to the other side and comes back. Two of these bumps is a full period. This is its time on one side of the planet. This is its time on the other side. And this right here, the height, it is the semi-major axis. In arc seconds, we'll have to convert it into something more useful. But semi-major axis and period, you can read off of this graph. Okay. Now off of this graph. So back to the tool. And then you fit it. And again, this is where more data is helpful, but it's 4 parameters. The amplitude, which is the semi-major axis, the period, phase, and then a tilt. So you need at least 4 data points, ideally 5. So I normally start by bringing the amplitude down to near the top of the data. There are little scroll wheels here for fine adjustments. Then maybe I'll shift phase over here, and then I'll shrink the period till it kind of fits the data. Might have to use the fine adjustment there. So that's pretty good. And then last bit is the tilt. Neptune, it's not edge on, it's more face on. And so the moons never cross the planet, they orbit around it. And if it was exactly face on, and if the orbit were circular, the distance would always be constant. But there's some tilt. I think it's a 30-degree tilt and 30-something degree. And I can play with it more. I can spend a lot of time really fine-tuning it, making sure every point is going through the data. And it's worth it for the students to do that, because any small error here in the period and semi-major axis, remember when you compute the mass, it's one of those numbers cubed, a cubed over p squared. So those errors get amplified 5 times with those powers. And so doing this really precisely pays off the mass measurement. But it's a fun little tool, and you just determine the orbit. Okay. They record the semi-major axis in arc seconds here, the period in days here. Now this next part, it's currently in 2 steps when it really should just be 1 step. And when I update this lab, I will combine it into 1 step. This lab's gone through multiple revisions in terms of how we do it, trying to make it cleaner, easier for the students. And this is kind of a holdover of 2 different techniques that we had previously. So we have to convert that semi-major axis into a physical size, AU. And so we need to first know how far away the target was, and that's here in stellarium. Well, here's Saturn at the time of the observation. We have not distance from the sun, but distance from us. It was 10.144 AU. In case of that Neptune data, it's 30.317. So they're going to use this geometry. And really what I should have them doing is taking the angle that they measured and having that be theta, and then figuring out the physical size that corresponds to it, the distance to the planet. But for whatever reason, I have them taking 1 arc second, figuring out what that corresponds to at the distance of the planet in AU. And that's a conversion factor between arc seconds and AUs, which they then apply to their measurement down here. Really, it should just be one thing. Instead of figuring out how many AUs are in 1 arc second at that distance, I should figure out how many AUs are within the angle they measured at that distance. And so these things will be combined in the next revision. Anyway, here's the same figure. We saw it in lab 2. We'll see it again in many labs, where the ratio of the angle that here's Earth, nothing to scale, of course, angle as a fraction of 360 is going to be proportional to the physical size as a fraction of the circumference of the big circle. So length over circumference is theta over 360, and the circumference is 2 pi times the distance away. So solving for the length here, you get 2 pi times the distance times theta over 360. They need to remember to convert their arc seconds to degrees to use this. The distance they looked up in stellarium, so then they get the length corresponding to 1 arc second, or in the future, the length corresponding to the semi-major axis. They record it here, and right now it's just a conversion factor from arc seconds to AU at that distance. They multiply it by the AU that they measured from the graphing tool, and they now have their AU and their semi-major axis in AU. And they convert from the orbital period from days to years, just divide by 365.242 if you want. And then they can very easily calculate the mass of the central body. It comes out in solar masses, but it's just that first number cubed divided by the second number squared. All these numbers would be small because moon orbits have periods much less than a year, and semi-major axes much less than an AU. And you get a small mass because the planets have masses less than the sun. And then we tell them the sun is 333,000 Earth masses, so they get their planet in Earth masses. That's a more reasonable unit for them to think about. And they calculate a percent error. Sources of error include how well Afterglow was able to centroid, or how well they were able to centroid if they had to do it themselves in case of the objects being blurred together. And then difficulty fitting the orbital parameters. And that can be difficult if they only have a few measurements. And actually, one thing we do tell them to do is once they have this, and they have a period, to go online and check it, Wikipedia, just confirm they're in the right ballpark, particularly if they only have 4 or 5 or 6 measurements. Really confirm the period, because overtones, let's see, half of this would be 2.91. Let's see what that looks like. Okay, so they didn't actually fit the data, but sometimes if you have a good fit with the period, then, yeah, often half the period. No, it's not half, it's twice. 10. Is that true? No, that's going to miss things too. Anyway, sometimes if you go to really short periods, you can also make it work. Now, yeah, some student could probably convince themselves that that fit all the data. And so we encourage them to check the period, particularly if they have a small number of points. You can easily get an overtone, like half the period or a third or a quarter. Yeah. Yeah, and that's that. And then you have this last bit here for the geocentric heliocentric bit. This one usually goes very well, and I'm particularly fond of it. It's fundamental astronomy, and it's pretty straightforward to do. Questions about it? Okay. Move on to lab 4, at least the part of lab 4 where we put in the observation for lab 5. Then if there's a few extra minutes, instead of diving into parallax, I'll tell you some MW stuff, because I had to explain it yesterday, so it's on my head. It's in my head. So lab 4, this is beginning of 2 labs, but really multiple labs on the cosmic distance ladder. In the cosmic distance ladder, it's these rungs. The first couple rungs are parallax rungs. And so here we learn how to do Earth baseline parallax, and we ramp our way up to stellar parallax, which with Gaia gets us halfway across the galaxy. With our telescopes, Earth baseline parallax will get you kind of out to Jupiter, maybe Saturn if you're really good. And I'm not sure how far out. It certainly works out to Alpha Centauri, but not too much farther. We're not Gaia, right? We're not in space. But they get the idea. Parallax, Gaia gets you out halfway across the galaxy, and then you switch over to standard candles. And in the next lab, they learn about R Lyrae, Cepheids, and Type 1As, where R Lyraes are lab 5 are good for galactic Milky Way scales, Cepheids to nearby galaxies, and Type 1As to far away galaxies. So we're learning how to measure it farther and farther out in the solar system, to nearby stars, across the galaxy, to nearby galaxies, far away galaxies. So these 2 labs, 4 and 5, really lean into that. And we return to the cosmic distance ladder with Hubble's law later on in the sequence. Lab 6 is an applications lab of standard candles. So there's a lot of this ties together now. Okay, so we'll cover this next time, but one of the key things is putting in your observation for lab 5. I'll bring up the observing guide here. So in lab 4, you put in the main belt asteroid observation for the class because it was tricky. It's hard to do. It requires TO access. So you did it for the class. Ideally, you did it in front of the class so they feel some ownership over it. This is the other instance where you're going to put in a single observation for a class. It's a sequence of 50 80-second exposures. That's 4,000 credits. That's more than any one student has. And so, you as the instructor, when I give you your group in Skynet, you have administrative controls. I give you extra credits, and you just assign them to yourself or to a student. If you want a student to come up and put the observation in, this one's actually pretty easy. Just it's 1 per class because it eats up a lot of credits. And so this is the first part of standard candles, the R Lyraes. So we're going to pick a globular cluster. We have a different one in fall, then spring, then summer. And these are all southern hemisphere because that's where our best telescopes are. Let's see the notes here. This is where to find it in lab 5, the video tutorial. It's a repeating observation. We've learned how to do those with lab 3. Recommend the instructor puts it in front of the class so they have a feeling of ownership over it. Select all available prompt telescopes in the south. And once complete, in others in the south if you want. Once completed, the instructor will let you know how to get to it in Afterglow, because it'll be in your folder, just like the parallax observations. They'll have to navigate to your folder. And then just the same as before, just kind of prodding the instructors to actually do this. If your instructor utterly and embarrassingly fails, do not fear. We do have data in the sample directory. But it's better if you do it in front of them so they feel ownership, at least partial ownership. So here in lab 5, it's down in this section, observe a globular cluster. Here's our fall target with the finding chart in different orientations, just in case their image comes back rotated or flipped or something. And there's an enlarge. They can click here to enlarge it to full size. The key thing is in the fall, we're going to be doing NGC 1261. I'm actually a little embarrassed about this. So in each of these, we have an R-Lyrae and a reference star. You can see them here. It's the summer ones. Summer one's a little tricky. I'm embarrassed because for my reference star, I actually picked a variable star, which is like the worst. So next time I update this, I will swap it out with the star right next to it. It's the same brightness, but it's not variable. So usually works fine, but sometimes it can mess with your results a little bit. Okay, so NGC 1261, let's see how to put this in. Add a new observation. NGC 1261. Search. There it is. Get our numbers to OPIS standards. Okay. And no advanced features. So it's observable in the southern hemisphere. Choose our filters. These have to be carried out in a specific filter. We use the V band. It's a standard candle, so we need to be able to calibrate it. So it needs to be in, it can't just be like high through or open filter. Those can't be calibrated against catalogs. Here, this can be. So we're going to do V band. And then it tells you to pick all the southern hemisphere prompt telescopes you have access to. I'll just click one of my orange circles here. And it included RCOP, and that's fine. Or I think it's down at the moment. And prompt 5 is down, but you can include it. You never know when it might come back. But prompt 6 is working. Meckering, I think, is back. Save and continue. Okay, and so what we're going to do, it is generic. We do 1 80-second exposure. And here you can see what that corresponds to on different telescopes, depending on their particular efficiency. And then as before, we're going to repeat this observation, this time 50 times with 1 hour. Be sure to change it to hours, otherwise you'll be waiting 50 days. And so we'll do probably 8 of these per night, and then it says continue on next available telescope if interrupted. So it may then hand off to the Australian telescope. You may only have a short gap, and you may pick up some more during the Australian night, and then it hands off to Chile. But over the course of 3, 4, 5 days, you should get all 50 observations. It's okay to have gaps, because in this, when we actually do the analysis, they're going to learn about period folding. And so even if there are gaps, you can fold it and get a folded light curve and see the whole pattern. So I'll submit this one. Got to pick an account with some credits. Okay, it's being added to the database. Yeah, 4,000 credit observation. And again, it only takes 3, 4, or 5 days, so a week should be sufficient to get all or at least most of the data. Okay, and so you put that one in, and then you go into lab 4, where lab 4 will have a couple components. I'll just mention them, and then we'll do them next time. And then I'll spend the final few minutes showing you some cool MW stuff. The first component is a manual component where they actually measure the distance to something like at Chapel Hill. I have this nice long straight wall, and across from it, there's smokestacks on a nearby building, and farther away, there's a water tower. And so they measure the distance to 2 objects, just like a surveyor would. They use those protractors with strings from the globe version of Lab 2 and their straight wall. And ideal, if you want to do this component, you find a location on campus. And I like doing the manual thing first, so they really figure out, they really get a feel for what's going on. After that, they do parallax to that main belt asteroid. And then using archival data for reasons we'll get into next time, they do it to Venus and determine the AU. Once they have the AU, they do it to Alpha Centauri, doing stellar parallax. So that's what's coming up next time. Okay, I'll pause. Questions about any of that? Okay.
I have
oh yeah, go ahead.
question about this observation. So it costs basically 4,000 credits, and I don't have a single account with this much credit. So when I took this observation, I only took 30 out of 50.
Okay, let's find your group here.
It's underscore UNL underscore F24.
Okay, we're in manage credits, and you don't have enough, but you should have admin status. Let's see here.
Yeah, I use the admin account for this one.
Okay. Yeah,
And
so what you can do
3,600.
as admin, you have the ability to grab the extra credits here.
Oh, okay.
Yep. And assign them to anyone, including yourself. So I always give extra credits. And if you need even more, just let me know. And so to do it, and this is a perfectly good question. Everyone needs to know this. Here you are. You click on you, and you grant yourself as many credits as you would like. Would you like some more credits right now?
I already did an observation last week for this one.
Sure.
I'm not sure if I could do more.
But in
Okay.
future reference, if you have like a student who is really active and burnt through their credits, as I've said before, you don't want to punish them. You want to reward them for being enthusiastic. And so just give them more credits, or yourself for these big observations. And that's how you do it. You type in how much you want, as long as it doesn't exceed, and submit. If you have a student who dropped, you can also click on them and take their credits back and put it in the general pool. Or you can reach out to me and I can just give you more.
Okay, thank you.
Sure, great question. Other questions? Okay, and we'll just wrap up. I'll give you a little MW teaser. I had to do a presentation to the DoD yesterday. So I had to prep these slides. And I always show them what module that we've been working on. Maybe I'll make this big. So the MW curriculum is almost done. There are 13 modules. We have versions written for 12 of them, 11 of which I have versions I've written myself. And the last one we're doing, it's not the last in the sequence. It's actually the first big rating. So the MW curriculum, for those of you who don't know, it's the follow-on curriculum. Now, once you get comfortable with the OPIS, if you have an opportunity, it fits nicely with second semester astronomy courses in particular. If I'm ever teaching our Astro 102 again, I'm totally throwing out the textbook, and we're going to just do this. And well, I have a course specifically for this, but if I didn't, I would take my Astro 102 and just turn it into this, where you learn many of the key lessons of stars, galaxies, cosmology, well, stars and galaxies anyway, but totally through doing instead of reading and doing word problems and whatnot. Anyway, this is module 4A. It's partway through the sequence. They've done some introductory stuff, a little taste of optical, taste of radio in the solar system. They've done a unit on star formation. They've done a unit on stellar evolution. And this is meant to take place during bright time when you can't do optical. So this is their introduction to radio. And they're using, this telescope right now, and eventually we'll have 4 more that we're currently integrating. This is the Green Bank 20 meters, 6 stories tall, 150 tons, 20-meter dish. And bigger than most of the largest optical telescopes, but that's considered a small radio telescope. And each team, the classes in MW are broken down into teams of 4 typically, and they work together throughout the semester. In this case, each team maps a chunk of the galactic plane, like a 20-degree by 20-degree chunk, or a couple of them if you have a smaller class. So this is a 20-degree chunk, 20 by 20 chunk, and so forth. And then all the groups can piece them together, and they have this map of the plane of the galaxy at radio invisible wavelengths. And for the chunks that they were responsible for, they zoom in and identify the objects. And here I've just pointed out some of the big ones, but we have this catalog and they match. We're building a tool to help them easily match it up and say, oh, what's this? And it's usually a star forming region, a supernova remnant, or a supermassive black hole at the core of a galaxy. And so they're discovering, we know of all these things, but they themselves are going through the process of discovering the invisible universe and making it visible, making it so you can see it. You can actually do photometry, measure brightnesses and things like that. And so they go through this process of exploration. As a class, they make a source catalog of the invisible universe, at least around the plane of the Milky Way. So it's a nice introduction. At my summer program, this is what we start with. This is like the project everyone's thrown into on day 1, and it evolves into kind of the more detailed projects. Anyway, once the students have done this in module 4B, we have them take the brightest sources and go back and make tiny maps around them, but red, green, blue maps. Of course, there's no such thing as red, green, and blue at radio wavelengths, but if our eye worked at radio wavelengths, we colored the longer wavelength red, the shorter wavelength blue, the middle wavelength green, you can make color pictures. So here are kind of the 6 brightest sources in the sky. In radio, you have crappy resolution. Everything's a Gaussian blur. But these are properly RGB color calibrated. And the color gives you information about emission mechanisms. So here we're teaching about thermal, which comes out blue. Think of something that's peaking up above the radio. Anything with any temperature is peaking up above the radio. So you're in the Rayleigh gene's tail. So you get a lot more short wavelength radiation than long. So it appears blue, kind of like an O star. Star forming regions tend to be blue to white, and then and those are bremsstrahlung emitters, and synchrotron emitters like supernova remnants and supermassive black holes are white to red. And you can see that progression here. That's supernova remnant, supermassive black hole, supernova remnant, supermassive black hole, all synchrotron sources. That's a bremsstrahlung source, and that's a thermal source. So from color, they're learning about emission mechanism. And the other thing they can do is they can follow up targets, galaxies, and do Doppler mapping. There's an emission line, 21 centimeter emission line we make use of. And like here's Andromeda, which is 3 degrees across, which is, here it is in the optical. Here, it's just big enough for us to resolve with our crappy radio telescope, because in radio, everything's very blurry. But we can map the Doppler shift of those lines. And so this side is moving away from us. This side is moving towards us. You can see the rotation of the galaxy. And from that, you can calculate things like its mass and its motion towards us. And then they do other galaxies, which they can't resolve, but from the spectra, they see the emission line broaden. And from the broadening of the line, they can calculate masses. And from the motion of the line, they can calculate Hubble's constant because they're being carried away by the Hubble flow. So these are some of the activities they do in 3 of the 13 modules in MW. 6 are visible modules, 6 are radio, and 1's a gravitational wave module. So just, I had a few minutes and I just had it in my head since I displayed it, presented to DoD yesterday. So just teasing it a little bit, hoping that some of you would be interested. We'll be putting in an MW focused grant, $2 million grant to NSF next summer, and hoping to bring along a lot of our current OPIS users, and there'll be participant program with funding there as well. Here's another fun slide just to kind of wrap it. But here are two, we have that Green Bank 20-meter telescope here already integrated, wedged into the Skynet 1 system. And then we're integrating 4 more, 2 of them here, 26-meter, you can see it in the back, and a 14-meter that we're almost done refurbishing. These are both in Hobart, Tasmania. If anyone's interested, we're having the next Robotic Telescope Science Research Education, RTSRE meeting in Tasmania in September of next year. So if you want to go abroad for an education meeting, that'd be a fun one. Okay, I'll shut up if there are any questions about MW or anything else.
Dan, just to clarify, the MWU versus the follow-along curriculum to the OPIS, or
They're the same.
they're same? Okay.
Yep.
All right.
Yeah. The follow-up curriculum is called Astrophotography, the Multi-Wavelength Universe, and that's where the MW comes from.
Okay. And when are you planning to do training for that?
So great question. Yeah. Up until this point, the meeting, basically everyone who's been an OPIS instructor at least once swaps, they switch over if they want, most of them do, to the MW development group for the past 3 years. We've had really good funding. Educators have gotten $3,000 a year for their contributions there. Of course, that has now ended. But so those meetings have been development. And so we're going to switch over to training in the fall, in the spring. And so it'll be OPIS training like you're doing now every fall, and MW training every spring. I teach it in the spring. It's best taught in the spring, just given how the sky works. We go from solar system to nebulae to galaxies. And for southern telescopes in particular, the spring semester, the sky works out along that sequence.
Okay.
So
So spring 25.
Yep, spring 25. I'll be doing training.
I thought you had said something previously about spring, and then a moment ago I thought you said fall. So I just wanted to get clarification.
Sometimes I sometimes say fall when I mean spring. It's a mental something's mentally wrong with me, and on that one I keep getting them backwards.
I was going to say it. I just want to make sure I wasn't going crazy, but then
Yeah.
again, it doesn't necessarily mean I'm not. So
Well,
thank you, sir.
we're all trying to maintain some level of sanity. All right. Well, if there's nothing else, I'm going to let you out a minute early. We're not going to go over today.
Well, I
Okay,
guess
so-
I have one kind
Okay.
of side question.
Yeah.
For your astronomy class, what percentage of the grade do you put into the labs?
Yeah, so at UNC, the lab is a standalone course. And so the labs are, they're 9 labs, so it's 90% of the grade. The other 10% are quizzes and extra credit things. If I were doing this integrated into a regular course, I would probably take a non-traditional approach. As we talked about at the Chapel Hill meeting, I really think with introductory astronomy, since they're never going to remember any of the content anyway, since they don't use it in their day-to-day life, we should really, to the degree that we can, flip this around and have like a lab first and then lecture as needed to make the lab parts make more sense approach. We don't have to cover everything in the textbook because they're going to remember almost nothing. So you can focus and drill down deep in these areas and they just do the stuff. So if it was integrated, it would be, I'd probably make it 2/3 of the grade, just off the top of my head, maybe even more. But that's me. This is kind of a new way of thinking about it. The traditional way would be, well, it's 1/4 of a 4-credit thing. But if I'm ever teaching a mega section again, I'm going to flip it around. It's going to be mostly lab driven.
Worth mentioning for those that weren't there, the summer sessions were recorded, discussions were recorded and are online on YouTube as well.
Yep, just email me and I can find you the link. We have a playlist. There's good stuff. And we crowdsourced a 100-page document. We came up with 30 dangerous questions in astronomy education. Why are we doing what we're doing, and what should we be doing moving forward, given the changing landscape? And we came up with more, but we only had time to discuss 30. And that document's now written. We crowdsourced 100 pages in 3 one-hour writing sessions, which is amazing. After 2 days of discussion, so it's insightful stuff that was written. My team has finished editing it, and we're now shopping it around for journals. And it should be a seminal document in where astronomy education is heading and why that's so different from where it has been and currently is. And it can't hurt when we ask funding agencies for more millions of dollars either to have that behind us. It shows that we're players in the game, and like serious. So hopefully that'll help us get more money to keep doing this fun stuff.
I think it was incredibly insightful. My 2 cents.
It's a cool conference.
Yeah, the whole thing. My pair of copper lingots.
I'm not promising to do it again anytime soon. It was a lot of work. Anyway, okay. Well, I lied. 2 minutes over. So I'll see you all next week.
Thank you.
Thanks.
Thanks, Dan.
Thanks. My pleasure.